Before the huddle, before the calls, before the snow closes over them, there is one impossible object. An egg balanced on a father's feet. The ice beneath him holds, for now. It's fast ice, a platform frozen to the continent's edge, locked to the coastline by ice shelves and grounded icebergs. Unlike the pack ice that drifts with wind and current at the margins, fast ice stays broadly stationary through the polar winter. But it's part of a larger, restless system. Pack ice grinds and shifts beyond the colony's horizon. Polynyas tear open and seal back shut in the dark, and the whole mass is poised to fracture when the season finally turns. The egg sits on the most stable thing available in this place. Relatively stable. At -35 degrees, in the dark, in the wind, with nothing else on offer. Above the egg, a fold of skin is the only nursery Antarctica allows. If you want to understand why emperor penguins endure the coldest place on Earth, don't start with the cold. Start with the thing they can never put down. The egg weighs roughly 460 grams. Pale greenish-white, vaguely pear-shaped, approximately 12 centimeters long by 8 centimeters wide. Its shell is relatively thick compared to most birds, some protection against the handling it requires. That weight sounds meaningful until you know the female who laid it weighs between 22 and 30 kilograms at breeding time. This egg is roughly 2.3% of her body mass, one of the smallest egg-to-body ratios among birds. Emperor penguins are the largest penguins alive, and they invest that enormous body into producing this comparatively small container. They lay one, only one. The entire genus Aptenodytes, emperors and their nearest relative, the king penguin, is the only penguin group that lays a single egg per breeding attempt. No clutch, no second chance within the season. If this egg fails, this year fails. The female laid it in May or early June, and then came the moment the entire breeding system depends on most: the transfer. Watch it happen, or imagine it from the fieldwork descriptions, because it's the most precarious transaction in Antarctic biology. The female, after laying, stands with the egg resting on the ice between her feet. The male shuffles toward her, angling himself carefully. He needs to get the egg onto his own feet without either bird dropping it onto the ice surface. They are large, round animals in the dark, operating with feet rather than hands, on a surface that offers no grip and no warmth, in temperatures that can fall well below -30 degrees. The egg must move from her feet to his in a matter of seconds. Some pairs drop it, some crack the shell in the transfer. What happens then matters. Brief contact during careful handling is survivable. The risk to the embryo inside rises with duration of exposure, not with the fact of contact itself. A dropped egg resting on the Antarctic sea ice is cooling toward the embryo's lethal threshold with every passing second. Field observers have documented that eggs accidentally dropped in the crowded colony are essentially lost. No other male scoops them up. They are simply abandoned on the ice. There is no rescue protocol here. The egg either makes it across in the moment of transfer, or it does not make it at all. When the transfer succeeds, the male draws the egg back onto his feet and pulls a fold of feathered abdominal skin over it in a single movement, the brood pouch closing like a curtain. The Australian Antarctic program documents what happens inside that fold as almost immediate. The egg presses against the brood patch, the bare, blood-rich strip of skin at the center of the pouch's interior, and the male's active physiology begins the work of holding the temperature steady. The brood patch isn't simply skin. It's a bare, highly vascularized area where blood flow is continuously and actively regulated, flooding warm blood toward the shell from underneath. Not a blanket, not a windbreak, a living heat exchanger, an organ engineered over millions of years to transfer metabolic energy directly from a parent's circulatory system into the developing life resting against it. The Australian Antarctic program has measured egg temperature during incubation at approximately 38 degrees Celsius. Outside temperatures at Antarctic colonies can fall well below -35 degrees Celsius. The gradient between the incubating surface and the surrounding air runs to more than 70 degrees, maintained not by passive insulation, but by continuous physiological effort. That gradient must be held for approximately 9 to 10 weeks. The female leaves within hours. She walks toward the open ocean across the fast ice. Sometimes the distance to the nearest open water from the colony is 50 kilometers. At hatching time in July, it can exceed 100 kilometers, sometimes more. She disappears into the polar darkness, and the male stands where he stopped. He won't eat again for months. The colony around him numbers in the thousands. Here at Point on the Adélie land coast, the world's longest continuously monitored emperor penguin colony, with breeding data going back to 1952, reportedly around 2,600 pairs breed each season. Halley Bay on the Weddell Sea coast held between 14,000 and 25,000 breeding pairs. The British Antarctic Survey's 2009 satellite census, the first global survey, estimated approximately 238,000 breeding pairs across roughly 50 colonies distributed around the full Antarctic coastline, all of them on land-fast sea ice. All of them selected because fast ice provides what nothing else here provides: a flat, seasonally reliable platform near the continental margin, close enough to productive foraging waters, stable enough to stand on through winter. When the platform fails early, breeding fails completely. Between 2016 and 2018, Halley Bay experienced 3 consecutive catastrophic seasons when unusually early fast ice breakup sent underdeveloped chicks into the water before they had waterproof feathers. They drowned. In 2022, record-low Antarctic sea ice across multiple colonies triggered what Peter Fretwell and colleagues at the British Antarctic Survey described in Communications, Earth and Environment as catastrophic breeding failure on a regional scale. The ice isn't a neutral backdrop. It's a structural condition. The colony must last. Everything depends on it lasting long enough. From colony arrival in late March or April through the female's return in late July or early August, the male emperor penguin does not eat. Total fasting duration, roughly 110 to 120 days. The physiological work of René Groscola, whose research on long-term fasting in penguins is the primary scientific reference on this question, describes males fasting for up to approximately 4 months across the breeding period. A male arrives at the colony weighing approximately 38 kilograms, having spent the preceding weeks in intensive feeding at sea. Hyperphagia, the deliberate, systematic loading of fat reserves against the fast to come. By the time his mate returns, he may weigh as little as 18 kilograms in the leanest cases. That is roughly 20 kilograms of body mass burned as fuel across 16 weeks of Antarctic winter while standing nearly still in the open air. Groscolas's research established that the fast proceeds in 3 physiologically distinct phases. A brief first phase burns carbohydrate reserves. The long second phase, the one that carries most of the winter, runs almost entirely on stored fat while actively minimizing protein catabolism. Muscle and organ tissue are protected while fat does the metabolic work. This is the physiologically safe period. The body's metabolic rate is suppressed, dialed to its lowest viable setting, preserving essential structures. Then, when fat runs critically low, phase 3 begins. Plasma urea and uric acid rise. Protein catabolism accelerates. The body, running out of stored energy, begins to consume muscle and organ tissue. A male entering phase 3 must refeed or face damage that can't be undone. The egg must hatch before that point. The female must return before that point. The breeding calendar is, at its deepest level, a race against stored fat reserves, a countdown running in the male's body from the moment the female walks toward the sea. One small thing affects the odds of winning that race. May snowfall. The 39-year satellite and biological dataset analyzed by Sarah Labrousse and colleagues in Biology Letters found that hatching success was non-linearly related to the proportion of days with snowfall in May. The most probable mechanism, males eating snow throughout incubation, supplementing their water intake and reducing dehydration-driven abandonment. Field observers at Point Géologie had independently documented males eating snow throughout the incubation period. A May snowstorm in Antarctica tilts the survival odds of the chick inside an egg that hasn't yet hatched. This is what precision looks like in a biology shaped by extreme scarcity. Every variable that touches the timing, female departure date, colony distance from open water, snowfall in May, propagates forward through weeks into the odds of a chick surviving. Standing in the dark with an egg on his feet, the male isn't still. This is the fact that high-resolution video analysis changed, and it matters. For their 2011 study, Daniel Zitterbart, Barbara Wienerker, James Butler, and Ben Fabry set up cameras at an elevated position near the Neumeier Research Station, trained on a colony of roughly 2,000 animals. Air temperatures that day ranged from -33 to -43 degrees Celsius. Wind speed reached 8.3 meters per second. Most of the birds were carrying eggs. No chicks had hatched yet. The females had not returned. The researchers recorded for 4 hours and analyzed individual bird trajectories. What they found was published in PLOS One in 2011, and it rewrote the image of the incubating penguin as a frozen sentinel. Every 30 to 60 seconds, a wave moves through the densely packed huddle. It begins when one bird makes a small step, 5 to 10 centimeters, the rough compression depth of the surrounding plumage. That step pushes slightly against the adjacent bird. That bird, no longer able to remain stationary, takes a small step of its own. That step passes the compression onward to the next bird. The signal travels as a directed wave at a few centimeters per second through the entire mass. The researchers described the packed huddle as reminiscent of a jamming transition in compacted colloids, similar to the physics of dense particle suspensions in materials science, where molecular scale movements propagate as pressure waves. After the wave reaches the far edge of the huddle, the whole structure settles back into its closely packed state and waits for the next wave. Over hours, those tiny propagating waves produce something remarkable: large-scale reorganization. Individual birds that started on the exposed outer edge of the huddle work their way slowly toward the interior. Birds that have been warmed in the center migrate gradually back toward the periphery. Nobody planned this. No emperor penguin is directing the process. The wave is emergent, the cumulative product of thousands of individual thermoregulatory decisions, each one made on local conditions, each one driven by that bird's immediate experience of warmth or cold, the whole system producing a collective result that benefits every member of the group. Zitterbart's team described a treadmilling pattern. Birds preferentially join the huddle at its trailing edge and leave at its leading edge, so the entire mass drifts slowly across the ice surface, orienting away from the prevailing wind. From a distance, from above, from a drone or camera, the huddle looks nearly motionless. At the level of individual bodies, it's in nearly constant, coordinated motion. The Natural Historian blog, summarizing the video from Zitterbart's supplementary materials, put it simply: they remain in near constant motion, with penguins at the leading edge that is experiencing a cold wind continually breaking off and circling around to the back. Field temperature measurements document what this collective motion produces. Caroline Gilbert and colleagues found interior huddle conditions above 0 degrees Celsius for more than a third of huddling time, with maximum recorded interior temperatures reaching approximately 37 degrees Celsius, close to human body temperature. Outside air during those same observations averaged -17 degrees. Separate work by André Ansel and colleagues measured the core temperatures of huddling birds at 35.7 degrees on average, about 2.2 degrees lower than isolated birds at 37.9 degrees, consistent with genuine metabolic conservation. The huddled bird is burning less because the thermal burden is shared. The body slows its burn. It costs less to maintain warmth when 10 birds per square meter are pressing together against the same cold. Up to 10 birds per square meter in the densest cold weather huddles. Studies by Gilbert and colleagues found that daily body mass loss in huddled birds runs roughly 40% lower than in isolated individuals. Without those savings, the male's fat reserves would be exhausted too early. He would reach phase 3 depletion before his mate returned, face the choice between the egg and survival, and leave. The huddle isn't supplemental to the breeding system, it's what makes the breeding system arithmetically possible. The huddle is the reason the number adds up. Late July. Somewhere in that dark mass of shuffling, slowly drifting bodies, one egg cracks from inside. The chick uses a small, hardened protrusion on its beak, the egg tooth, to break through the shell from within. The process takes hours. From the outside of the brood pouch, nothing visible changes. The male can feel it, perhaps, the slight shift of weight, the warmth altered in some marginal way. Then the shell opens. Mean hatching date at Point Géologie, approximately July 20th. Based on long-term field records going back to Prevost's foundational field study of 1961. Mid-July, deep Antarctic winter. The sun, if it appears at all at this latitude, barely clears the horizon. The temperature hasn't shifted. The wind hasn't slowed. What has changed is this. The egg is now 2 animals instead of 1, and the smaller of them is completely helpless. The endocrine study by Lorme and colleagues, published in Hormones and Behavior, describes the newly hatched chick as non-homeothermic, unable to regulate its own body temperature. The Australian Antarctic program specifies that this capacity takes approximately 50 days to develop. 50 days from hatching before the chick can generate enough metabolic heat to maintain its own temperature. For every one of those days, thermoregulation is entirely the responsibility of the parent holding it. When chicks were experimentally separated from parental contact and exposed to ambient air in physiological studies, they shivered immediately and vigorously upon exposure. Antarctic air against a newborn emperor penguin chick isn't an inconvenience. It's lethal on a timescale of minutes. At hatching, the chick weighs a few hundred grams. The down coat it arrives in is thin, not yet adequate for independent warmth. It fits beneath the same fold of skin that held the egg for the past 9 or 10 weeks. The same brood patch, the same vascularized heat exchange surface, now providing warmth to a living creature instead of a developing embryo. The male draws the fold closed. The chick disappears back into the warmth, but the male now has a problem his body has been quietly accumulating for weeks. He has one remaining resource, and it won't last long. Under the influence of prolactin, the same hormone that drives parental behavior across many vertebrate groups, the lining of his esophagus has been producing a nutritive secretion during the late stages of incubation. Rich in fat and protein, sometimes called crop milk, by analogy with the secretions produced by pigeons and flamingos, though it evolved independently in this lineage. The male feeds the newly hatched chick this esophageal secretion across a period of roughly 3 to 7 days. He tilts his head back slightly, regurgitates a small amount into the chick's open bill. The chick swallows. The male does this again. That is the window. 3 to 7 days. After that, the secretion is exhausted. The male has nothing left to give. He has been fasting for close to 4 months. His body is at somewhere approaching half its original mass, and the secretion he is feeding to the chick is essentially the last metabolic reserve he is capable of producing. If the female does not arrive before those days run out, the male faces what the ecological literature describes plainly: He must refeed to survive. He would have to leave the chick. A chick left in the Antarctic without parental brooding dies within minutes. This isn't a corner of the story. This is the architecture of the entire breeding system made visible. Everything, the timing of the fast, the distance the female must travel, the energy she has stored at sea, the route she takes back across the ice. Everything has been built around the need to close this gap of 3 to 7 days. Female emperor penguins don't return when convenient. They return when the male's reserves have nearly run out, because the breeding season can't be any shorter than it is. The egg takes 9 to 10 weeks to hatch. The fast takes roughly 16 weeks from arrival. The female's foraging time is whatever remains between those two constraints. She returns because the calendar of the male's body demands it. When she arrives, she calls. In a colony of several thousand birds, standing in the dark, the female returning from the ocean must find one specific male. He has no fixed address. The huddle has been drifting slowly across the fast ice for 2 months. There is no nest, no landmark, no territory she can walk back to and expect to find him waiting. Emperor penguins are the only penguin species that breeds on sea ice rather than on stable land, which means they are also the only penguin species that must solve the recognition problem without any topographical cues at all. In 2000, Thierry Aubin and Pierre Jouventin published the mechanism in the Proceedings of the Royal Society B. The emperor penguin syrinx has 2 branches, left and right, that produce 2 distinct fundamental frequencies simultaneously. Those 2 simultaneous frequencies interfere with each other, generating a beat pattern. That beat pattern is individually unique, as specific to each bird as a fingerprint, varying in its temporal and spectral characteristics in ways that are consistent across time and detectable by other birds across the noise of a colony. Aubin and Jouventin wrote it directly. Being unable to use topographical cues and identify its partner visually, the emperor penguin seems the best acoustic model for studying individual recognition. The habitat stripped away every alternative. No fixed site. No visual marker that persists across the winter. Only the call. Playback experiments confirmed the mechanism precisely. Suppress one of the 2 simultaneous frequencies and recognition fails. The individual identity is carried by the combined interference pattern, both voices together, both frequencies simultaneously. Earlier computerized acoustic analysis, published in 1993, confirmed that individual specific cues reside in the temporal and spectral characteristics of each bird's call, and that these cues are consistent and sufficiently distinctive to serve as identification across a noisy colony environment. Against that continuous sound, across what can be hundreds of meters, after 2 months apart, a female locates the specific bird she is looking for. She calls. Somewhere in the shuffling mass of birds, he hears the specific 2-frequency interference pattern that his nervous system learned in April, that he hasn't heard since she walked toward the ocean months ago. He answers. His answer carries the same dual-frequency signature. She orients toward it. She calls again. He answers. The Australian Antarctic program's description of this process is understated. It's remarkable how quickly a female can locate her mate among thousands of penguins when she comes home. She finds him. She presses against him. She wants the chick. He is reluctant. Field reports describe males as notably resistant to handing over, even when visibly depleted, as though the body's circuitry has locked onto the object of its months-long custody. Eventually, she takes the chick, tucking it beneath her own fold of skin. The recognition runs again in a different direction. The chick she has never seen before, which has been alive for days, which she didn't watch hatch, which she has never heard, produces its own call. She learns it. Parent-chick recognition in emperor penguins is acoustic, not visual. Research on king penguins, which share the same 2-voice vocal architecture and the same colonial breeding context, confirms that parents identify their own chick's individual call amid the continuous noise of thousands of other chicks. For emperor penguins, the same structural necessity applies. There is no visual marker, no nest, no fixed location. The bond between parent and chick is made in sound, because in this environment, sound is the only reliable bond that exists. The colony is loud for a reason. Thousands of birds are simultaneously running this search, calling, answering, orienting, calling again. The noise of an emperor penguin colony in July is the noise of the system working. Every call is an identity. Every answer is a confirmation. The chaos is the mechanism. With the female holding the chick and the chick's immediate starvation risk suspended, the male turns toward the ocean. He has been standing on that fast ice platform since late March or early April. He has fasted for as long as 16 weeks. His body has burned through roughly 20 kilograms of stored mass, from approximately 38 kilograms at arrival to something approaching 18 in the most depleted cases. He moves across the ice at whatever pace his diminished reserves allow, heading for open water, for the krill and fish his body is demanding at a cellular level. August becomes September. The female feeds the chick from what she has carried in her stomach across the ice. Both parents now alternate foraging trips, one at sea, one at the colony with the chick, each return timed around what the chick needs and what the ice allows. By September, chicks have developed a thick down coat and are gaining mass rapidly, demanding that both parents forage simultaneously. Left alone at the colony, chicks press together in creches, running the same collective thermal logic the adults run in the winter huddle. Individual thermoregulatory decisions, emergent group warmth, no coordination required. By early December, black patches of adult feathers appear on their flippers. The down begins to shed in patches. The chick is developing waterproof feathers, the prerequisite for entering the ocean. Without them, cold seawater penetrates directly to the skin. Without waterproof plumage, the ocean is lethal as fast as the open air. The timing of this development isn't accidental, and it isn't arbitrary. What is happening underwater during those same weeks is the reason the breeding season begins in the dark of May. All winter, the southern ocean beneath the seasonal pack ice has been in near total darkness. The sea ice zone, which in September covers between 18 and 20 million square kilometers of the southern ocean, intercepts solar radiation before it can reach the water below. Beneath the ice, algae cling to the underside, slow metabolizing through the dark months, held in suspension by the cold, waiting. Below them, the water column is cold, dense, stratified, and dark. As the austral spring advances through September and October, solar radiation returning to the southern ocean strengthens week by week. The seasonal retreat of sea ice, which occurs primarily across just 3 months, November through January, losing more than 15 million square kilometers of coverage in that window, exposes the ocean surface to direct sunlight for the first time in half a year. The physical changes arrive in a cascade. Meltwater from the retreating ice, fresher and lighter than seawater, creates a shallow, stabilized surface layer that traps light near the top of the water column. Ice algae that have been holding on under the ice edge bloom as sunlight reaches them. In the open water immediately behind the retreating ice edge, phytoplankton blooms build on the nutrient-rich water that has been accumulating through the winter, concentrating the Southern Ocean's annual primary production into a few weeks of intense biological activity. Research on Southern Ocean biogeochemistry has confirmed that ice edge phytoplankton blooms focus most of the region's annual primary productivity into this brief growing season, providing the phytoplankton stocks that the food web requires to function. The limnology and oceanography literature on under-ice algae documents that ice algal concentrations increase dramatically at the onset of spring, seeding the open water blooms that follow ice retreat. Antarctic krill, Euphausia superba, are the pivot of everything that follows. They graze on ice-associated algae under and along the ice edge through winter and switch to open water phytoplankton through spring and summer. Their reproductive success tracks ice conditions. Their abundance in any given region in any given year is closely tied to how much ice there was and when it retreated. Krill are the primary prey of emperor penguins, Adelie penguins, Weddell seals, crab-eater seals, minke whales, humpback whales. Every large marine predator in the Southern Ocean has krill somewhere in its diet chain. The explosion of krill abundance in spring isn't merely a food source for penguins. It's the foundation of the entire Southern Ocean food web, the event that makes everything else possible for every creature in this ecosystem. Emperor chicks typically fledge in December and January. When the timing holds, when fast ice persists long enough for chicks to develop waterproof feathers, when females can return on schedule, when the male's reserves last long enough to bridge the gap, the chick that enters the ocean in early summer arrives when the Southern Ocean is at its annual peak of productivity. The water it swims into is thick with krill. The bloom is at or near its height. The chain from phytoplankton to krill to penguin closes at exactly the moment it needs to. Natural selection tuned the emperor penguin's breeding schedule to Antarctic seasons over geological time. The alignment isn't mechanically guaranteed. The catastrophic failures at Halley Bay from 2016 to 2018 and the 2022 regional collapse, documented by Fretwell and colleagues via satellite, make brutally clear what happens when ice retreats before chicks can fledge. The chick enters the water without waterproof feathers, and the ocean kills it as quickly as the air would. The alignment is probabilistic, seasonally driven, under constant pressure from a changing climate. But the underlying architecture of the timing is real and specific. A breeding season that begins in May, a fast of roughly 4 months, a hatching date in July, a fledging date in December. Each stage timed against the next, the whole chain timed against the Southern Ocean's annual awakening. 1 egg, 1 fold of skin, 4 months of Antarctic winter. Every tool in the emperor penguin's biological arsenal, the fat reserves built through hyperphagia before the fast begins, the 3-phase fasting metabolism with its long protein-sparing plateau suppressing the metabolic burn, the brood patch actively flooding warm blood toward the shell across 9 to 10 weeks, the emergent wave mechanics of the huddle redistributing warmth through the mass every 30 to 60 seconds, the 2-frequency acoustic fingerprint that cuts through the noise of thousands, the esophageal secretion that bridges the 3 to 7 day gap between hatching and the female's return, serves one purpose: buying time. Not defeating the cold, not escaping it, not shortening the winter, outlasting it, specifically, precisely, just long enough for the season to change. The huddle buys the fast a few extra weeks of physiological viability. The brood patch buys the egg another hour of warmth during a blizzard. The call buys the reunion that restores the chick's food supply. The esophageal secretion buys the days between hatching and the female's arrival. Each tool hands off to the next. Each one gains the breeding pair a little more time against the season. Endurance isn't a consolation prize in this biology. It's the only form of strength this environment permits. The cold can't be fought. The dark can't be shortened. The distance the females must travel can't be reduced. What can be done is outlast, precisely, efficiently, without waste, the body calibrated to its exact reserves, the timing calibrated to a season that will eventually turn. The egg stays above the ice. The call finds the family in the crowd of thousands. The chick enters the brutal world with a thin coat of down and a nervous system that can't yet generate its own warmth. The male crosses the ice toward the ocean, burning the last of his reserves. The parents trade shifts across the austral autumn. Chicks grow heavier, their down shedding in patches, real feathers darkening beneath it. At the margins of the fast ice, the pack ice begins to fracture. Swell and warming push into the ice edge. Solar radiation floods the water column for the first time in half a year. Ice algae bloom at the retreating edge. Phytoplankton bloom in the stabilized surface waters behind the melt. Krill swarm in open water. The Southern Ocean, which has been lying dormant through the polar night, wakes into its most productive season. And the chick, now feathered, now waterproof, now barely resembling the helpless gram-weight animal that hatched in the July dark, enters that ocean at the exact moment it has been timed, across millions of years of evolutionary pressure, to enter it. What looked like one father holding one egg in the dark turns out, from a sufficient distance, to be something else entirely. A precisely timed act of endurance connected to an entire ocean waking up. The personal and the planetary joined at the level of a single breeding season. Subscribe for more stories like this.